Hello, my name is Shahriari, and this is a lecture based on my book Retrolinear. The topic of the lecture is contraction theorem and dimension. We have already defined what a basis for a vector space is. The basis is a set of elements that span and are linearly independent. Our main question today is how do you construct a basis for a vector space? One method would be to start large, start with a spanning set, a collection of vectors that you know span that might not be linearly independent. Then you try to winnow it down, to bring it down, make it into a basis. This is the basis of what's called the contraction theorem. The second method would be the other way around. Start small, start with a linearly independent set, maybe nothing, and then just start putting in vectors, but be careful at every stage to keep it linearly independent until you get to a basis. And that's the basis of what we call the expansion theorem. Along the way, we will want to know one very important thing, that all bases have the same size for the same vector space. For so-called finite dimensional vector spaces, and we'll talk about what that means, all bases have the same size. And because of that, the number of elements in a basis will be called the dimension of the vector space. After we know that all bases have the same size, we can know that this number, the number of elements in a basis of a vector space, is a constant. It's something that's not going to change from one day to the other, or what you had for breakfast. And therefore, we can give it a name, and it ends up being a very important parameter for our vector space called its dimension. In this lecture, we're going to focus on the contraction theorem and the idea of dimension and why all bases have the same size. It's not a priori clear at all why two different bases for the same vector space will have to have the same number of vectors in them. Here's the theorem that is the basis of everything else that we do. So let's say we have a vector space. We have a set of vectors, n vectors in this vector space. W is the span of this set S. W is a subspace of V. Assume that one of these vectors, the ith one, for example, was a linear combination of the ones before, V1 through Vi minus 1. Then what we might do is we might throw that element out. And what this theorem says is that when you throw that one element Vi that was a linear combination of the ones before away, the span does not change. The span is still W. That's intuitively pretty clear. The reason for this is that if you have some vector and if it's a linear combination of V1 through Vn, meaning that it's in W, then maybe you use Vi in that linear combination. But if you did, you can replace it with some linear combination of V1 through Vi minus 1, because Vi is in the span of V1 through Vi minus 1. And therefore, that vector that was already written as a linear combination of V1 through Vn can also be written as a linear combination of V1 through Vn without using Vi. That's basically the proof. But because this theorem is one that we use quite often, and because I want to have a little bit of practice with the idea of span that we have been using all along, I will give you a slightly more formal proof also. Again, W is the span of V1 through Vn, and Vi is a linear combination of the ones before. That's our assumptions. Let U be the span of V1 through Vn, but without Vi, after Vi has been thrown out. And what we want to show is that U is the same as W, W being the span of V1 through Vn. Now, first of all, these vectors other than Vi, they're all in W. In fact, Vi is also in W. But because these vectors are in W, their span stays in W. Whenever you have a set of vectors in a subspace, the span stays inside that subspace, can't get out. Why? Because linear combinations of elements of a vector space stay in that subspace. And so because of that, U being the span of these guys is inside W. On the other hand, Vi is in U also. Why is that? Well, because Vi was the span of V1 through Vi minus 1. And those guys are in U. So Vi is in their span, and so is in U. And so that means that not only V1 through Vn without U, Vi are in U, but Vi also is in U. And again, if those guys are in U, their span is going to be inside U also. And the span of all of them is W, so W is a subspace of U. And so U and W are the same, because U was inside W and W was a subset of U. So we gave two proofs of this little fact, that if you have something, a linear combination of the ones before, and throw it out, the span does not change. Now, this is the basis for the contraction theorem. What does the contraction theorem says? The contraction theorem actually just says that if you have a vector space, and if you have a finite set of vectors in that vector space, and if you know that this set spans, so you walked into a vector space, you picked as many elements without really thinking about linear independence, but as many elements as you could, just making sure that it spans that vector space, then some subset of S is a basis for V. So after you pick your spanning set, you can go and call that, throw some of them out, and get a basis. Basically, it says that you never have to say, I'm sorry. Like if you pick a whole bunch of elements that was a spanning set and you were looking for a basis, it's not like you look at your collection and say, you know, this guy's just not going to work. Let's throw it out and start over again. You never have to do that. You can just look at the collection you have. There might be some extra stuff, you throw them out, and you get a basis. Now, this is what the contraction theorem says. But in fact, what's really important is the proof of the contraction theorem, the argument behind this, which tells us how to do this, how to go from a spanning set to a basis. And for that reason, I'm actually going to include the proof in the statement. In fact, what I'm going to say, what you're going to do is fix an order for your set S. Your set S was a spanning set, just pick an order for it. Go through elements of S in order and one by one. Just start from the first one, second one, third one, fourth one. And for each one of them, ask a question. If the first one is the zero vector, throw it out. If not, keep it. Then go on to the next one. Is that a linear combination of the first one? Is the third one a linear combination of the first two? And at each stage, if any of them is a linear combination of the ones before, throw it out. The point is, if you throw away the zero vector at the beginning, or if you throw away any of these vectors that were a linear combination of the ones before, by the theorem we just proved, the span does not change. So the remaining set still is going to span S. You're never going to come back. So when you look at an element and you check, is it a linear combination of the ones before? If the answer is no, it's not, you say, fine, keep it. You go to the next element. If that one is also not a linear combination of the ones before, you keep it. If it is a linear combination of the ones before, you throw it out, and then you move forward. You're always moving forward. So eventually, this is a finite set. S is a finite set. You will get to the end of it. And at that point, after you have checked the last element, you will have a linearly independent set. Why? Well, because at that point, the first element is not the zero vector, and none of the vectors are a linear combination of the ones before. And we have proved the theorem in the linear independence lecture that if you have a set and no element is a linear combination of the ones before, and the first one is not the zero vector, it's linearly independent. And all along, the span did not change. The original set was spanning S, and as you went along your set, you had a spanning set as well. Because all you did was, at worst, you threw away something that was a linear combination of the ones before, and that does not change the span. So by the time you're done, you will have a linearly independent set that also spans, and therefore you have a basis. The second paragraph, you can think of it as a part of the contraction theorem, but really the contraction theorem is that first paragraph. The second one is really the proof, but this is really what's important, this process, this argument. Okay, let's look at an example. Let's say that we are looking at the vector spaces of functions from R to R. And every element of this vector space is one function. So y equals sine of x could be one function. Y equals x squared could be one function, one element of this vector space. One function that I'm interested in is f of x, is this function that's -1 if x is less than 0, and it's 1 if x is greater or equal to 0. I'm also interested in the function g of x that's -1 if x is less than -1, and 1 if x is greater or equal to -1. And I've drawn their graphs on the right. Also, I'm interested in this function h of x, which is 0 if x is less than -1 or greater or equal to 0, but between -1 and 0, it's 47. And finally, I have this other function that it's -4 if x is less than -1, it's 0 between -1 and 0, and it's 4 for everything greater or equal to 0. So these are 4 functions that I'm interested in. My vector space is functions from R to R. I have a set F, G, H, and K of elements of S. Now, each one of these things, you might think of them as a function. You plug in X, you get Y. One of these is just one point in this vector space. Every one of these is one element of this vector space. W is the span of S. These are elements in a vector space. You can find their linear combinations, and you get a subspace. Span of any set of vectors in a vector space is a subspace. So the span of these 4 functions is a subspace, and I want to know what the basis is for this subspace. And so I'm going to use the contraction theorem. So first of all, what are my functions? Here they are for the record. And they're listed in this order, F, G, H, K. If you don't like the order, you can change it, but you've got to fix the order once for all at the beginning of the process for the contraction theorem. You can't move them around while you're doing it. And as you're going along, because when you get to the end, you want to be sure that you have checked everything is not a linear combination of the ones before. The first thing you ask is f, the first one, the zero element of the vector space. Is it the zero function? No, it's not. Zero function would be y equals 0, f of x equals 0. This is not it. The second question is that, is g of x a linear combination of the ones before? And that means, is g a scalar multiple of f? Can I multiply f by 5, by 7, by -3, by square root of 2, and make that function turn into this other function, g of x? And the answer is no, you can't. If you multiply f of x by some constant, it does change f, but it doesn't shift where it switches from -1 to 1. And so the answer is no. Note that there are quite a few values in which f and g's are equal to each other, like f of -58 is the same as g of -58, and f of 58 is the same as g of -58, but that's irrelevant. The question is that, can I find one scalar that when I multiply by the function f, I get a new function, and that new function is g, and the answer is no. Okay, then the next question is that, is h a linear combination of the ones before? It's not that is h a scalar multiple of f and scalar multiple of g. It's a more complicated question. Is h a linear combination of those two? Well, how do I know? Well, I might say that, well, if it is, then that means that this function h of x should be alpha times f of x plus beta times g of x for every x in R, because the function h of x is supposed to be the same as the function alpha f plus beta g. Not at one point, but the whole function has to be the same. So that means that if you plug in something for x, for h, you should, and plug in the same thing for alpha f plus beta g, you should get the same thing. So for example, you can plug in 0. If you plug in 0, h of 0 is 0, and f of 0 and g of 0 are both 1, and so you get that alpha plus beta equals 0. You can plug in other things, and you get other equations like that, and you can solve them, and you get that h of x is -47/2 f of x plus 47/2 g of x. Now, by plugging things in, that doesn't necessarily say that this is true, because it might be that if you just plug something else, you realize that, that there's a contradiction, that there's too many conditions that have to be satisfied, and this cannot be done. So after you plug in a variety of things and figure out what alpha and beta might be, you have to actually go and show that this, the function on the left, h of x, is the same as the function on the right, -47/2 f of x plus 47/2 g of x. And you can do that. And so how do we do that? Well, we say, look at h of x. H of x has 3 different definitions based on where x is. If x is less than -1, h of x is 0. If x is less than -1, what is f of x? Is -1. What's g of x? That's also -1. And if you put -1 for f of x and g of x, you will get 47/2 minus 47/2, so you get 0. So they agree. You do the same thing between -1 and 0, and for greater or equal to 0. And you will get, so for example, between -1 and 0, if you plug something in for f of x, something less than 0, you get -1. But for g of x, you get 1. So, so you get minus times -47/2, that's 47/2, plus 47/2, so you get 47. And you also check for things greater than equal to 0, not just for one thing, but for all things greater or equal to 0, the two sides are going to be equal. So h of x is a linear combination of the ones before. What do? The contraction theorem tells us throw it out. So h is thrown out. Then we go to k, and we ask, is k a linear combination of the ones before? Now, mind you, h is out. H is not there. So the question is that, is k a linear combination of f and g again? And you do the same process, and you get that, yes, k of x is also a linear combination of 2f plus 2g. Is a linear combination of f and g, meaning that it is 2f of x plus 2 of g of x. Again, you have to check that. And because it is, you throw it out. You got to the end, and now you know that f and g, those two things, are a basis for w. So this was the contraction theorem in action. Okay. Now, now I want to prove a theorem that allows us to define dimension. And this is going to be the sort of the workhorse that will prove for us the thing about dimension. So, but I'm going to say something a little slightly more general. So let's say V is a vector space, and let's say that you have a spanning set. And let's say you also have a linearly independent set, a different set. They might share some elements, but they may not. But I've got a set that spans, another set that's linearly independent. The set that spans has n things in it. The set that's linearly independent has m things in it. This very important theorem says that m is always less than or equal to n. In other words, you cannot have a linearly independent set that has more elements than a spanning set. At most, they tie. But linearly independent set might have fewer elements than a spanning set, and they could tie, but it couldn't be the other way around. You can't have a spanning set that's smaller than a linearly independent set. Well, what's the proof of this? So again, we have a set we call S0, which V1 through Vn, which spans, and we have this other set, which is linearly independent. The proof is a proof by contradiction. And so we assume that we wanted to prove that m is less than or equal to n, that the number of things in the linearly independent set is less than or equal to the number of things in the spanning set, but we're going to assume the opposite. So how is that? Like, why are we going to do that? Why are we going to assume something that we suspect is false? Well, this is for the sake of argument. For the sake of argument, we're going to say, well, what if m was greater than n? Then our logic is going to be impeccable all the way down. And at the end, we'll get something that doesn't make any sense. And we'll say, well, our logic made sense. So what was wrong? The thing that was wrong was this assumption that we made right at the beginning. And therefore, this assumption is wrong. And if m is not greater than n, then it must be less than or equal to n. And the proof is done. This is the way proof by contradiction works. You somewhat unintuitively assume the opposite of what you want to prove. Okay. Now, a lot of proofs in linear algebra, or at least elementary linear algebra, are of the follow your nose variety. So what do I mean by that? What I mean is that you usually say, well, what I want to prove, like for example, I want to prove something is linearly independent, or I want to prove something is a basis. And then you ask yourself, okay, that's what I want to prove. How do I prove that? Well, to prove linear independence, you have to write a set of linear combination equals to 0, put the scalars equal to 0. To prove that's the basis, you have to prove it's linearly independent and spans. So you sort of tell yourself how you prove such a thing, and then you start proof. Then you just say, okay, well, if I'm proving linear independence, I'm writing this linear combination equal to 0. Then I look and see what I have. And if I use the stuff that I have, then it'll end up being that the scalars are 0, and then I've proved linear independence. You pretty much can follow, what do I have to prove? How do I prove that? And then what do I know? And then you will get there. Sometimes proofs are not like that. Proofs that have real content are not like that. You have to have some insight, like some idea that if you just sort of look at it and don't try different things, you're never going to come up with. I mean, it's just not going to be the obvious thing to do. So in this case, this is the idea. The idea is that we make a new set, which we call A1, which is the same as S0, except for one change. That we took the first element of our linearly independent set and stuck it at the beginning of S0. So W1 was stuck right at the beginning, and now we have W1 comma V1 through Vn. So what can we say about this set A1? First of all, it spans V. Why? Well, because S0 already did. The V's already spanned. We stuck in this extra element. That's not going to hurt. Still spans V. And this other element was also in V, so it's not going to give you something new. It's just going to be in V. But also, it's going to be, this set is going to be for sure linearly dependent. Why? Well, because W1, V1 through Vn spanned V, and therefore W1 is a linear combination of V1 through Vn. And so this set is linearly dependent. But I'm going to insist on this order. I want W1 to be at the beginning. If W1 was at the end of the set, then you would say, okay, W1 is a linear combination of the ones before. That's why it's linearly dependent. Well, throw it out. I don't want you to throw it out. So that's why I'm putting it right at the beginning. And because of that, because it's linearly dependent by contraction theorem, or at least by the proof of the contraction theorem, or not really by either one of those, by the fact that it's linearly dependent and the theorem we proved about linear dependence, an element of A1 is linearly dependent on the ones before. But what we're doing is using the process that the contraction theorem told us we are doing the same thing. So one of them is a linear combination of the ones before. Well, could it be W1 is the zero vector? And that's why the thing that should be thrown out. No, because W1 is sitting inside a linearly independent set. And the zero vector cannot be inside a linearly independent set. If zero vector is in any set, it's already linearly dependent. So it can't be W1. Must be one of the other ones. Because it's linearly dependent, one of them is a linear combination of the ones before. Can't be W1, must be one of the V's. Well, throw it out. If you throw it out, I mean, I don't know which one it is, but let's say S1 is remaining set, and without loss of generality, let's say it was V2. Like, it doesn't matter which one it is. I should really say it's VI, but then it just becomes complicated writing it down. So let's just say that it's V2 that you threw away. So now, and let's call that set S1. So what can I say about S1? Well, S1 still spans V. Why? Because of the theorem we proved at the beginning of the hour, that if you have an element that's a linear combination of the ones before and you throw it out, the span does not change. So the span doesn't change. Okay. What we have really done is we have done an exchange. We have exchanged W1 for one of the V's. We brought the W1 from the linearly independent set, put it in S0, in our original spanning set, and got rid and exchanged it for another one. We kept the size of S the same, but we did this exchange, and we're going to do it again. This time we're going to bring W2 in, and we're going to put it right there. So we're going to put W1 and W2 at the beginning, and then the remaining V's, because one of the V's is gone, it's going to be there. What are we going to say? Well, this still is going to span because without W2 still span, and it's going to be linearly dependent because W1 through Vn, S1 spanned all of V, and therefore W2 is in their span. So W2 is in this linear combination of the other ones, and so this set is linearly dependent. Again, we know by our criteria for linear independence that if a set is linearly dependent, either the first vector is the zero vector, which we know it's not, or one of them is a linear combination of the ones before. Could it be W2? No, because W1 and W2 were sitting in that linearly independent set, and in that set, none of them was a linear combination of the ones before. So they're still not. So again, it must be one of the V's. So again, you get to throw it out. And so again, you've exchanged, this time W2, for another one of the V's. And what we're going to do is we're going to continue. We're just going to keep doing this. We're going to, one by one, bring the elements of W in, and that set, after we bring the guy in, the set still spans, but it's linearly dependent. Something must be a linear combination of the ones before. It has to be one of the V's. Throw that guy out, and the span doesn't change. And then you continue doing that. Eventually, now remember, M is greater than N. Eventually, every element in S0 will be substituted. So all the V's will be replaced. And so we will have that Sn is W1 through Wn, and the span of this set is V. So we have now replaced every one of the V's, and we got that. So what? I mean, there's nothing wrong with that so far. But the question is that, what about the next guy? Remember, M is supposed to be greater than N. So when you look at the list W1 through Wm, you can't stop at Wn. There's more, maybe a lot more, but at least one more. So, and what about that next guy, Wn plus 1? That's supposed to be in the I mean, that's in V, so it's a linear combination of W1 through Wn. So it's a linear combination of those other W's, but W1 through Wm was supposed to be linearly independent. It can't be a linear combination of those guys. So this guy is not in the span of Sn, but the span of Sn was supposed to be V, and that's a contradiction. So the contradiction proves that there's something wrong. It wasn't our logic. Our logic was impeccable. So it must have been that assumption at the beginning that M is greater than N. Therefore, M is less than or equal to N. So this does the heavy duty work for proving, and this is maybe the more interesting theorem that we've proved so far, the most interesting theorem we've proved so far, because again, the idea of this exchange thing was a clever idea. Okay, so what? So now I'm ready to prove to you that all bases for a vector space have the same number of elements. So let's say V is a vector space, and let's say S and T are both bases for V, different bases maybe. Assume they're finite sets so that I can talk about size. then, by the way, if they're infinite, there's a corresponding theorem, which we will maybe talk about much later in the lectures when we talked about cardinality. But for now, we're only worried about finite sets. So assume S and T are finite sets. Then the number of elements of S is going to be the same as the number of elements of T. So two bases cannot have different number of elements. So what's the proof for that? Well, we're going to use this notation, which we have used actually before, that if you have a set, then when I write absolute value of X, although I won't say that, I'll say the size of X is the number of elements of X. So the absolute value sign for a set denotes its size, how many things are in that set. Okay. So S and T, as we said, are both bases. So they will have this conversation. S says that I span V. I am a spanning set. Well, why? Well, because I'm a basis. And S will tell T that you are a linearly independent set. I'm spanning, you are linearly independent. By the theorem we just proved, I have at least as many elements as you. That size of S is greater or equal to T. But then T comes back and says, well, I span V also. I'm a basis, so I span, and you're linearly independent. So I have more elements than you, greater or equal to elements as you. Because both of these statements are true, the only way out is if there's a tie and they're the same size. Okay, so because of that, we can define dimension. So V is a vector space. We call V finite dimensional, either if it's the zero vector space, the vector space that just has one element is the zero vector, or if it has a finite basis, a basis with finite number of elements. And otherwise, if that's not the case, we call V infinite dimensional. Now, if V is finite dimensional, meaning that it has a finite basis, then the dimension of V is the number of elements in a basis of V. You have used dimension maybe willy-nilly before, but now we have a precise definition of what the dimension of a vector space is the number of elements in a basis. And because of the theorem we proved, that's well defined. It's not like if I find a basis, I might decide that the dimension is 5, but you may decide that the dimension is 6. Or today, I find a basis with 3 elements, and tomorrow I find a basis with 4 elements. The size of the basis is always the same. And we denote this thing by dim V. Now, if it happens to be that the field of scalars is something strange or different, or if you want to emphasize the field of scalars, then, and V is a vector space over F, remember that means that the scalars come from the field F. For first time listeners, F just is the real numbers, the scalars are real numbers, but we have discussed that the scalars can be other things. In that case, if instead of dimension of V, we write dimension of V sub F. That sub F will tell you that the scalars are F. And also note that dimension of the zero vector space is 0, because we had previously said that a basis for the zero vector space, we had said that we want it to be the empty set, actually basically for this reason. The empty set has no elements in it, so if the empty set is the basis for the zero vector space, then its dimension will be 0. That's just by fiat. That's what we just have decided that because that helps with other things to call this a zero-dimensional vector space. So let's look at some example. Dimension of Rn is n, and the reason for that is that if you look at the standard basis, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, and so forth. There's n elements. That's the standard basis, and it has n elements. That's reassuring. Like R3 is 3-dimensional. That it would be not nice if that wasn't the case. R2 is 2-dimensional, and so forth. But now we sort of have a reasoning for that. Okay. Polynomials of degree less than or equal to n. Their dimension of that vector space is n plus 1. And the reason for that is that a basis for it, the standard basis for it, is 1x, x squared all the way to x to the n. And there are n plus 1 elements in there. Polynomials of just polynomials with real coefficients, that's infinite dimensional. A basis for it is 1x, x squared, it goes on forever, and that has an infinite number of elements. So we said that something is infinite dimensional if it doesn't have a finite basis, and so this guy is infinite dimensional. Dimension of vector space of matrices, 2 by 2 matrices, is 6, because here's the basis for it. In fact, we call this the standard basis also. There's 6 elements in this basis. They're linearly independent and they span. And so the dimension of 2 by 3 matrices is 6. That's a 6-dimensional vector space. Okay, let's do another example. Let's say that we are looking at W, which consists of a bunch of functions. Which functions? Functions that you can write in the form alpha plus beta sine squared x plus gamma cosine squared x plus delta cosine of 2x. These are all functions from R to R. The domain is R. You can plug in any real number you like, and the answer will be some real number. Alpha, beta, gamma, and delta are also real numbers. Okay, so this is my W. If you take S to be 1, sine squared x, cosine squared x, and cosine of 2x, these are 4 functions in functions from R to R. These are specific functions. The first one is the function y equals 1. The last one is the function y equals cosine of 2x. And clearly these span W. Span of S is W. If you write a linear combination of these, you get that typical element. And so this, by the way, says that W is a subspace of the functions from R to R, and therefore we can look for a basis. So is S linearly independent? Well, how do I know? Well, I go through what the contraction theorem told me to do. Go through the elements and try to see which one is a linear combination of the ones before. The first one is not the 0 function. 1 is not the 0. Y equals 1 is different than y equals 0. But sine squared plus cosine squared is 1, which means that cosine squared x, which is the third function, is a linear combination of the ones before. It's 1 minus sine squared x. So we throw it out. Now, cosine of 2x is cosine squared x minus sine squared x. But remember, cosine squared x we already threw out, so it's not there. But that doesn't matter. Because cosine squared x is 1 minus sine squared x, we can plug that in, and we can write cosine of 2x in terms of 1 and sine squared x. So cosine of 2x is also a linear combination of 1 and sine squared x. So we throw that guy out also. And so we know that if we have this set, this is a spanning set. Now, I never really, well, maybe I did say that sine squared x is not a linear combination of 1, but that actually needs a little proof. So how would we prove that? You would write, well, maybe alpha plus beta sine squared x could be 0. Maybe there's some trig identity that I'm not aware of. And so what you do is you plug in different values for x. This has to be, that 0 is the 0 function. Alpha plus beta sine squared x equals 0 function. And so no matter what x I plug in, the two sides have to be the same. So if you plug in x equals 0, you get sine squared of 0, 0. So you get alpha equals 0. And then you plug in x equals something else, and you will get that beta is 0. Like, for example, if alpha is 0 and x is pi over 2, you get beta times 1 is 0, beta is 0. And so that means that t is linearly independent. And so t is a basis for W, and in particular, the dimension of W is 2. This is the end of this lecture, and we will talk about the expansion theorem in the following lecture. Here's a picture of Claremont for those of you who miss Claremont.